Algebra 2, Module 1, Test Preview. My Algebra 2 honor students, in a few days hence, are going to be having their Module 1 test, and I wanted to prepare a preview that's going to cover the vast majority of what is on this test. And here are the topics that are tested, and these are, I believe, all of them. Domain and range and inequality, set and interval notation, end behavior, restricted domains, writing a linear function relating the amount over time, increasing, decreasing intervals on graphs, finding average rates of change from data in a table, finding intervals of positive, negative values from set notation information, finding a line of best fit from data in a table. That's going to be a calculator-based problem. Graphical transformations, fitting a quadratic function to 3 points. That's going to be kind of challenging. We haven't done that enough to where I'm super comfortable, but between this lesson and what we're going to cover in class, I hope we get some additional pieces. Then finding inverse function relations from graphs, tables, and equations. That's going to be at least 80% of what's on this. And most of this preview I've really taken from the test itself and just made some slight modifications. Use the graph shown to answer directions. Here we have this graph here in light blue. Write the domain of the function as an inequality using set notation and interval notation. Basically, inequality notation. We have our domain is, I hope you can see, we are going to the left, or coming from the left and going toward the right. And so in inequality notation, we would write that as x is greater than negative infinity, yet less than infinity. So there's your inequality notation. And sometimes in the book they've had us put plus infinity. I'm not as worried about that. Next, set notation, very similar to inequality notation. X such that, okay, otherwise it's just like inequality notation. X is greater than negative infinity and less than infinity. And sometimes you see that with the script R, but I'm not worried about that. And finally, interval notation is going to be greater than negative infinity, less than infinity. Okay, next we have write the range of the function as inequality using set notation and interval notation. What we have is we have a lower limit or boundary of 0 right on the x-axis. So we can write this in inequality notation is y is greater than or equal to 0. Okay. And in set notation, we can write that as y such that y is greater than or equal to 0. And finally, in interval notation, we can write that as bracket, open bracket 0, comma, infinity. We are going up toward positive infinity. So that's going to be that one. Next, describe the end behavior of the function. Okay, here it is. We're going to go to the right. As x approaches infinity, what does f of x approach? As x goes positive to the right, what does y do, or f of x do? Well, it also approaches positive infinity. And next we're going to take our other end behavior as we go to the left. As x approaches, this time not positive infinity, but negative infinity, f of x approaches what? Does it go toward negative infinity? No, we're going up again still. So we are approaching positive infinity as we go to the right and to the left. And lastly, what is the range of the function if its domain is restricted to between -5 and 1? And so if we go on this graph here to -5, which is between -4 and -6, so we're going to go right to here. That's one thing we're looking at. And this domain is restricted to 1. Okay, well, 1 is going to be right here. So the range of this, in this box here, we're only looking at this piece here. I'm just boxing in. This is all we're looking at, right? Actually, it's even less than that. It's only this much, right? Because we're not even going any higher than that. And it's not even this thing down here, oops, because we have a lower boundary of the x-axis, don't we? So we're just going to the boundary here. So our range is going to be, again, and we can use it in the same thing. Our range, I'm going to put R colon, we're going, our range is from 0 minimum to a maximum of 4. So I'm going to say a range over this same domain is going to be 0 to 4. And we bracket off here. And yes, this could be written in inequality notation. You could write that as y is greater than or equal to 0, or and less than or equal to 4. You could write it that way too. But I like doing it because we have the same type of notation as it originally was delivered. Next, a student rides her bike every 3 miles every 15 minutes for 2 hours. Write a function that models this situation, determine the domain for the situation, identify the range using a notation for domain range. Well, we have to look at our units for this, right? We got minutes, but we got hours every 15 minutes. So what are we going to use? I'm going to want to use hours. And so 15 minutes, how many hours in 15 minutes? You should know that 15 minutes is equivalent to 1/4 or 0.25 hours. So we're gonna go with that. So our domain is going to be, we'll write that first. We started writing, so we're going to go in hours. We're going to go 0 to 2. That's our domain, right? And then our range, I guess I'm doing the easiest part first. We're going 3 miles every 15 minutes. So 3 miles every 15 minutes. So she's going to go 3 every 15 minutes, every 0.25 hours. So that's going to be 3 times 4 in 1 hour, so 12 hours plus another 12 hours. So she's going to go from 0 mileage to 24 miles within 2 hours. Okay, so we've done that. We've written interval notation. Write a function that models the situation. So we could do this in terms of x and y, just to show you what this might kind of look like. If we have hours here, and we have a distance here in miles. Well, we know we went 24 miles because we figured that out, and we know we went 2 hours. So this might be a path if you retained a constant speed. I guess that's what it implies. She went 24 over 2 miles per hour. So we can say, if we call this x and y, we can say y equals 24 divided by 2 x, and 24 divided by 2 is 12. So we have y equals 12x. Okay, and does it say anything about units? Well, we're going to get our units for this are going to be miles. Y is miles. X equals hours. Okay, well, we've already identified that with the graph. So this is miles, hours. Yeah, that'll be fine. So that should be enough. We got a function, and it would help to put the time element there. We have a domain and range. I don't know if there's anything else we need in here. And we've done this in interval notation, so we get all the points. Next, the graph shows units sold as a function of time. Using set notation, identify increasing and decreasing intervals. So as we evaluate increasing, decreasing, we go from left to right, and we should be able to see that the function is increasing or going up until x equals 3. Okay, that's x equals 3. We're going up till x equals 3. And now we are decreasing all the way until x equals 7. Okay, so using set notation, we will say increasing, decrease. So we'll say increasing on, meaning on the interval. It looks like, and we're talking about x values, x such that between 0, x equals 0 and 3. Okay, 0 is less than, well, t, right? T is, so t all the way to t equals 3. And also from 7 to infinity, right? And x such that, and you know something, I'm getting the letters mixed up. I want to put t in there for this. Let me do that. Consistency might be helpful. So I'm going to say t such that t there, and also t such that, in this case, between 7 and infinity. So we could just say t is greater than or equal to 7. Okay, that would take care of that. Or we could sandwich it in between 7 and infinity also. Increasing and decreasing. Okay, that's increasing interval, and decreasing on, we're going to go between 3 and 7. So on t such that t is greater than or equal to 3, but less than or equal to 7. Okay, so we covered the increasing interval and the single decreasing interval. There we are. And that is in set notation. We've got to be flexible enough to really understand our set notation, interval notation, and inequality notation in this test. The table shows some of the values of the polynomial function. What is the average rate of change of the function over, so over the each, should be over each of the following intervals, from x equals 0 to x equals 1. Well, the rate of change is this. It's rate of change, average rate of change, which I'll put in the slope, that's what it is, the slope, is f of b minus f of a over b minus a. And we just use different things. So this first one from x equals 0 to x equals 1, well, I'm going to put b here for 1, put down here. B is equal to 1, a is equal to 0, and 20 is f of b, or the output where you have an input of 1, and 70 is f of a, so f of a. So for this, our average rate of change is going to be, I'll just write in m equals f of b, which is 20, minus f of a, which is 70, over 1 minus 0, which is, that's going to be negative 50 over 1. So I'm just going to call this, I'm just going to say negative 50, because negative 50 over 1 is the same as 50, okay? So that's that. From 1 to 2, you see we're going up 10, but b is up 1, so we're going to have, for this one, m equals 10 over 1, which equals 10. That's our average rate of change. From 1 to 3, we're going up from 10. We're going, in this case, f of b is going to be 10 minus 20 over b minus a. Well, that's going to be 3 minus 1. So we're going to have negative 10 over 2, which equals negative 5. That's our average rate of change. From x equals 3 to x equals 4, we're going to have m equals 90 minus f of a, which is 10, over 1 minus 0. So we're going to have 80 over 1, which is 80. So we can see that we have positive and negative average rates of change for all these intervals shown. Next, a polynomial function whose domain is all real numbers is positive with intervals, or what intervals are the function negative. So we have, what we have for a polynomial function is this. I'm just going to draw a sketch here. So it says positive from the intervals negative infinity to 2. So here's 2. That's a key point. Here's another key point given here. 4, a key x value, and then 9. It says here, polynomial function's domain is all real numbers. So what that's doing is we are positive from negative infinity to 2. So we're coming down like this somehow. I don't know exactly what it looks like. Some kind of polynomial is kind of a curve thing. So I'm going to do that. So I'm going to say we're coming down like this kind of. Okay. So we are positive all the way there, and also from 4 to 9. So we're positive here, like this. And then, because everything else has to be negative, I'm going to draw the negative parts in red. We have to be negative down here. And then also, from x equals 9 down toward positive infinity. So, over what intervals are the function values negative? Well, it's going to be, just by analysis, f of x, if we call this function f of x, is negative on the intervals. I'm going to use interval notation, 2 to 4, 2 comma 4, and also 9 to less than infinity. So that would be where the function f of x is negative. I think on the test, if I'm not mistaken, it asks you what are the values of the zeros. It's going to be the same sort of language, and you have to point out that the zeros you have zeros, and you can just put coordinate pairs here. You have our 2 comma 0, 4 comma 0, comma 9 comma 0. Those are the zeros of this polynomial function described by the text. Making a sketch like this could be quite helpful. Next, find the equation of the line of best fit for the data in the table. So we have, this is going to be a calculator thing here, and I don't have these things written down separately, so I'm going to have to kind of veer back and forth with my calculator as I do this. So x values are 1, 2, 4, 6, 7. So I go to the calculator, and second quit, and we'll go to Stat, Edit, and put 1, 2, 4, 6, 7. I think I got all those right. Next, I'm going to put the corresponding y values, and those will be 2, 7, 10, 15, 17. 2, 7, 10, 15, 17. 2, 7, 10, 15, 17. So that should be all of them. And to find the line of best fit, we go to Stat, Calc, 4, and we press Enter till we get ourselves an equation. So we're going to get y equals ax plus b. So to two decimal places, you would say a y equals 2.35 2.35x plus 0.82. And you can just put 0.82. And when it says write the equation, be careful. Because when it says equation, you got to have an equal sign. So don't just write the right side. And I'm not going to be too picky on how many decimal places you go out to. Try to get at least a couple decimal places, but I'm not going to be too picky about that. I want you just to be able to do this. 1, 2, 4, 6, 7. I'm going to make sure the points look right. I'll go back to my table. Stat, edit. 1, 2, 4, 6. Yeah, that looks good. And it's not asking us to make a prediction based on that or anything. That's going to be it, essentially, on it. Describe how to transform the graph of h of x equals x squared to obtain the graph of the related function f of x equals negative 2f that has x squared minus 2 plus f. Well, for that, this thing here, and the form for a quadratic function, we talked about that, is a times point x minus h plus k. And the negative is going to reflect this downward. So how is it going to happen? So h, which is, let's say h of x, is reflected about the x-axis, or downward, right? So that's one of the transformations. And then what is this negative 2 going to do? That is going to stretch vertically. I'm going to put this next stretch vertically by a factor of 2. Okay? Next, this minus 2 is going to do what? X plus is to the left and x minus to the right. It'll be translated two units to the right. Well, that's going to be squared up here, guys. And then it's going to be translated 6 units up. And then we could do this. And it says f of x squared minus 2 in parentheses. What that's going to look like when we graph it is this. It's going to be y equals negative 2, and we're going to put x minus 2 quantity squared plus 6. It's going to be, and then you can check using the calculator. Here it is. So go here, clear these things out from a previous video I did a minute ago. So we get negative 2, open parentheses, x minus 2, and we're going to quantity square that thing, and then we're going to add 6. It better be just as I mentioned here. Zoom safety standard window. And so yeah, we reflected this thing because originally, and I'm going to show the original function. It says x squared, right? I'm going to make x squared red. So x squared is the original function. You're going to have calculator in hand. So you take this red one, reflect it downward about the x-axis. We could do step by step here, couldn't we? We could reflect it. I'm going to reflect and stretch at the same time. Negative 2x squared. And blue, that's going to look like, see, we reflected it and stretched it, and then we translated 2 units to the right and 6 units up. Exactly as written here. So that would be our correct answer. This is the toughie here. The cable between 2 towers of suspension bridge forms a curve modeled by a parabola. In the illustration shown, unit of measurement is feet, and the vertex of the cable is point P. Find a quadratic function that models the cable and state the function's domain. Well, the parent function for a quadratic function is f of x equals a times point x minus h squared plus k. And here, at the point 0, 2, we have h is equal to 0. So, and then we have 2, so we're going to go up. So I'm going to rewrite this as f of x equals a, and we're going to have x, and x, we don't have plus or minus 0. So I'm just going to say f of x equals a x squared plus k, and k is 2 plus 2. Now, what we can do is use one of these other points to figure out what k is, and then we're going to have a quadratic function, and then we'll state the function's domain. But we should already know the domain, right? The x values extend from negative 24 to positive 24. So our domain doesn't say what type of notation. I'm just going to use the easiest I can find, which is notation. So negative 24, comma 24. That is our domain. You have that. Okay, now we're going to use this point here to find what a is, and that way we're going to get a quadratic function. Well, f of x equals, well, that's going to be our y value, so 10 is equal to a, because a is what we don't know, and x squared, well, x is 24, so we have 24 squared, a times 24 squared plus 2. Well, solving for a, we're going to have, we subtract, I'm going to put 24 squared times a plus 2 equals 10. And solving for a, if we subtract 2, we're going to get 24 squared, a equals 8. Now subtract 2 from both sides. And then if we divide, a is going to be equal to 8 divided by 24 squared. And I'm going to go to our calculator, get a calculator page, go second quit. Okay, 8 divided by 24 squared, so alpha y equals 8 divided by 24 squared. we get here 1 over 72. So that's going to be 1 over 72. And if you happen to get a decimal, you can change it to a fraction by, I'll show you that in class maybe. And so our equation is going to be f of x is equal to 1 over 72 x squared plus 2. And one thing we can do is we could test this in our calculator. And I go get a y equals. I'm going to clear these things out here. Clear. So I'm going to do this in red. So alpha y equals, enter. So 1 over 72. And we're going to put x squared. And then we're going to add 2 to that. And so we could graph this, see what it looks like. We don't see much because of the aspect of it. We don't have all the points that were in there. To do that, we'd have to get a window big enough. We'd have to go like negative 30, and we have to go up to 10. That's which next, and we'll say 30. Actually, we don't need that number, do we? We need like negative 12. The x is fine. It's the y that has to be higher. So x scale of 1, that's fine. Y minimum negative 10 is fine. Well, here we want to go up to 24, or what was it? 12. Yeah, we'll go to 20. And then we graph, that's what we see here. I'm not seeing it. I'm missing something. What am I missing? Oh yeah, the x has to be bigger and the y smaller. That's where I messed up. Okay, back here, let's go get our window again. I do need negative 30 here and positive 30 here. And now we're going to be good. The graph, yeah, it looks better. And the key thing is in the table view. Before I go to table view, I'm going to check. I'm going to do table start of 0 and delta table of 24. And you're going to see why that is. If I go to table view here, I see that at negative 24 we get positive 10. At positive 24 we get 10. So that matches all the points here. So this is going to be our answer for this one right here. And we'll have a chance to talk about this a little more in class, I hope. Find the inverse function f negative 1 of x for the function fx equals negative 1/3 x plus 5. And we have the 4-step process. Step 1 is we convert f of x to y. So negative 1/3 y equals negative 1/3 x plus 5. Next step, we switch x and y. So we get x equals negative 1/3 y plus 5. And I'm going to put negative 1/3 y plus 5 on the left equal to x. First step, subtract 5. So we get negative 1/3 x, negative 1/3 y, excuse me. Equals x minus 5. And to solve for y, if we multiply this whole equation by negative 3, and I'm just going to go down below here still, we're going to get, well, I forgot the negative 5 right now. That's 5, yeah, there we go. Now we're going to have y is equal to negative 3x, and then we have negative 3 times negative 5 plus 15. And then the last thing we're going to do is change this to f negative 1x. We say f negative 1 of x is equal to negative 3x plus 15. Is that right? I don't know. Let's check it out. Let's go to the calculator. So we have negative 1/3 x and then that's going to be about the line y equals x, and then we're going to have negative 3x plus 15. I think that's what it was, right? Negative 3x plus 15. Let's make sure I have these right. Negative 3x plus 15 and then 55. Okay, we'll check these out. Let's graph. Yeah, it's kind of hard to see. There we go. Okay, I'm going to go to zoom square just to get our aspect right. So this red one is the line y equals x, and you can, I hope, see that these two ones, this is going to be the negative 1/3 x plus 5, the blue one. The black one's going to be negative 3x plus 15, and they reflect about this line, this red line, y equals x. So that's going to be good. There will be a problem quite similar to this. Your test, and that's going to be all I have here. There'll be a few other functions or questions related to functions, inverse functions. That's going to be it. You do well on the content here. That test is going to work out great for you. Good luck, and thanks for viewing.